So, welcome to Robotics 1. In today's class, we are going to look at a robot. And in this robot, you will notice that you will have some exceptions to the rules. So, the robot that we would like to discuss in today's class is you have a revolute joint, then another revolute joint, but at the end of this revolute joint, you have a prismatic joint. So you have a prismatic. Now please understand, if the prismatic joint is in the horizontal direction, this is the robot which is R, this is R, this is R, this is P, RRP. So wherein you have R perpendicular to R, parallel to C. So you have the robot something like this. For some reason, if that prismatic joint is vertical, it means instead of extension being horizontal, if the prismatic joint extends in the vertical direction, that is the scalar robot. Everyone understood this? So you have this R, first revolute joint, second revolute joint, and the third joint is prismatic. But if that prismatic joint is actuation is in the vertical direction, then it becomes a scalar robot. So first and foremost steps is we have to identify the coordinate system. So let's start with the coordinate system. This is Z0, this is X0, this is Y0. Then here I'm gonna have a Z1, then I would have X1. So you have C1. Okay, let's start here. So now what I want to do is I want to assign the coordinate frame. Let's look at the rules. What is the rule number one? Rule number one is Z must pass through joint axis. Joint axis. Then second rule is V n minus X n should be perpendicular to Zn and must intersect Vn minus 1. And the third rule is we have to use the right hand coordinate system. Now, at this point, what I want to do is I want to identify what would be the position of X. So as you can see, X can go in the vertical direction and X can go in the horizontal direction. But if X goes in the vertical direction, it is perpendicular to Z1, but it's parallel to Z0. So this is the position. This is going to be X1. So now you can see X1 intersects with Z1 and it is perpendicular to Z1, and X1 intersects with Z0. Let's complete the triad. You have X, Z, and now this gives me Y. Y1. Now, these two frames I don't have problem with. This is the frame 0, this is the frame 1. Now what we need to do is we need to go to frame 2. And frame 2, the first rule is V has to pass through the actuation joint. So this is V2. Now let's talk about where the X2 could be. Now for X2, we have two choices. X2 could be somewhere here, or x2. So x2 could be somewhere here, or x2 could be somewhere here. Do you agree with me? So there are two possible locations for x2. So x2 could be pointing down, pointing up, pointing towards the paper, coming out of the paper. But the problem here is, in all these configurations, x2 is perpendicular to z2, but it is not intersecting z1. Why? Because please understand, no matter what plane you choose, whether your x1 is coming down, left, forward, upward, there is a parallel offset between this z1 and this x2. So z1 and x2, they are non-intersecting. Everyone understood this? z1 and x2 are non-intersecting. So clearly, in this particular case, no matter what you do, rule number 2 will be violated. Everyone understood this? Now, in this case, and this happens sometimes, what we have to do is, this is the trick. This is the trick. I want you to move this frame from here onto here. So the frame which was here needs to be moved over here. So we have to construct the frame. So this frame, so I will show you here, and I need to show you the end effector. This is the end effector. End effector. So frame Z2, X2, and Y2 needs to be translated. So I need to show this here for clarity. Okay. So right now the problem what we are having is I have Z1, I have X1, I have Y1, and then the next frame is here. So if I take Z2 over here, if I take Z2 over here, and if I have X2 either going up or going down, the problem is X2 is not intersecting with Z1. So what I need to do is, I need to translate the frame from this location all the way over here. So what I'm going to do is, I'm going to construct a frame is Z2, and then I need to construct the frame X2, and then as you can see, Z2, X2, so my Y2 is going to be like this, and I will explain this once again. So please understand, X2, Y2, and Z2 frame translated to X1, Y1, Z1 frame as rule 2 was not satisfied. Are you with me? Now, what I want to do is, initially my frame was here, rule didn't satisfy, so I translated the frame over here, and this is my new picture, wherein this is the frame X1, Y1, Z1. This is the translated frame X2, Y2, Z2. And now tell me, for this new frame, are the rules satisfied? The rules are satisfied because Z2, which is over here, is going to a joint axis. X2 is perpendicular to Z2 and perpendicular to Z1, and Y2 is forming the triad. Everyone understood this? Everyone clear about this? So if the rules are not satisfied, what will you have to do is you will have to translate the frame back. Now what that means is, let's look at the last frame, which is over here. This is the end effector. And on this end effector, I'm gonna have this frame which is I'm gonna call this V3, X3, and then I have this Y3. And what I want to show you here is this is my joint 2. This is joint 1. This is my joint 2. And on joint 2, there are 2 frames. And this is my joint 3. And on joint 3, I have C3, I have X3, and then I have Y3. And before I proceed further, I want you to confirm that for the frame X3, Y3, and Z3, all 3 rules are satisfied. Can you see Z3? It's an end effector. There is no joint. So Z3 can be anywhere, but for the sake of simplicity, I'm assuming Z3 aligned with Z2. Just for the sake of simplicity. It can be in any other direction. But since I want to make my life easy, Z3 is aligned with Z2. Now, X3 needs to be perpendicular to Z3 and X3 needs to be perpendicular to Z2. Can you see that X3 is perpendicular to Z2? And as you can see, you have X, you have Y, and you have Z. So can you see that you have X, Y, and Z? X, Y, and Z. X, Y, Z. So now align it with X, X, Y, and Z. Everyone understood this? So the coordinate system is set up. Now what we need to do is we need to work out the forward kinematics and inward kinematics. So what I'm going to do is I'm going to give you the distances A1. I'm going to give you this distance A2, and this distance is D3. So typically A1, A2, A3, A1, A2, A3 are the fixed distances. And these are the moving. So basically D change. D stands for displacement. So basically you have a displacement. Now what I want you to do is I want you to understand what has happened here. Initially, this frame was here. This is where the frame was. So this is where the frame was. But we moved this frame over here. So this distance is A2. And this distance is B3. No, sorry. This distance is A2. This is the end effector. This is the end effector. This is joint 3. And B3. Are you with me? So basically, this is the location of joint 3. But since when we constructed the frame here, it was violating the rules. So we translated the frame over here. And this is the end effector. End effector, end effector. Now we have to go through the same process of defining 0R1. So 0R1. And since the rotations are about Z, so this is theta 1, theta 2, and I have D3. So cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. And this is the rotation transformation. You need to have a projection matrix. And the projection is going to be x0, y0, z0, x1, y1, z1. As you can see, x1 is aligned with x0, y1 is aligned with z0, and z1 is aligned with minus y0. You okay with this? Everyone okay with this? So when I perform the multiplication, first row, first column, first row, second column, first row, third column, second row, first column, second row, second column, second row, third column. This is 0. Then third row, 0. Are you with me so far? Now with this, I need to find out 0h1. What happens in 0h1? In 0h1, we copy this matrix as is. Zero, 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 1, 0, 0, 0, 0. And here we find the distances. So here the distance between the frame 1 and frame 0 are about x0. Distance between frame 1 and frame 0 about y0. Distance between the frame 1 and frame 0 about the z0. So as you can see, here you have 0, and here you have a1. Then here is everyone okay with 0h1? Now what I need to do is I need to do 1 r2, and in 1 r2 again cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1, and then you have to have the projection matrix, and the projection matrix is going to be something like x2, y2, z2, x1, y1, z1. So now the question is, which x2 would you choose? Now for the purposes of calculation, x2 is coinciding with x1. Do you agree with me? Because we translated the frame. So you can see x2 is aligned with y1. y2 is aligned with z1. And z2 is aligned with x1. Do you agree with me? So please understand. For this, x2 is aligned with y1. y2 is aligned with z1. And z2 is aligned with x1. So you have this projection matrix. And then once you perform the multiplication, first row, first column, first row, second column, first row, third column, second row, first column, second row, second column, second row, third column, then first row, first column, first row, second column. Are you with me so far? Now please note, when we translated the frame 2 is on top of frame 1. So which means there is no translational distance. Frame 2 is on top of frame 1. Why did we translate the frame 2? We translated the frame 2 because the rules were not satisfied. So frame 2 is on top of frame 1. In that particular case, you will agree with me, all the translations are going to be 0. Because there is no translation between the frame 2 and frame 1. But for the sake of consistency, I will write this over here. So 1h2, so minus sine theta 2 0 cosine theta 2, cosine theta 2, 0 sine theta 2, 0 1 0, 0 0 0. I get 1 over here. And please understand, this is where you will have a 0 here, you will have a 0 here, and you will have a 0 here, because frame Q on top of frame. Do you agree with me? That's why all these distances are 0. Everyone okay with this? Any questions? Now comes the last joint. Now please understand, the last joint is a prismatic joint. There is no rotation. So when the joint is prismatic joint, rotation matrix is going to be identity. Everyone understood this? When the joint is prismatic joint, the rotation matrix is going to be identity. But please try to understand, the projection matrix still be present. Why? Because the previous coordinate transformation may not align with the new coordinate transformation. Which means even though the rotation matrix is identity, you will have a coordinate transformation. So, and I want to make this absolutely clear. So, for an example, I'm just going to write this down for my own satisfaction. 2R3. 2R3. Please note, this is going to be 1 0 0 0 1 0 0 0 1, because this is a prismatic joint, P joint. But even though it's a P joint, you are going to have x3, y3, z3, x2, y2, z2. So now let's look at x3, y3, z3. Can you see x3 is aligned with x2? 0, 0. Can you see y3 is aligned with y2? And can you see z3 is aligned with z2? Are you with me so far? So in this particular case, you get an identity matrix. But there is possibility that your projection matrix may have some negative terms, okay? Please be careful. When the roots are not matching or roots are not satisfied, you will have a combination of matrices, but projection matrix will be present in every computation. Now, the tricky part is this, and I want you to be very careful with this. So now the next part is 2H3. Do you agree with me? 2H3, the first matrix is going to be 0 0 1 0 1 0 0 0 0 1 0 0 0, and then I'm gonna have 1 over here, and now I'm gonna have the 3 terms to fill. Argument remains the same. What you have is distance between frame 3 and frame 2 along x2. Distance between frame 3 and frame 2 along y2. Distance between frame 3 and frame 2 along z2. So these distances will always be in the previous frame. So let's look at this. So here, can you see that this total distance, I want you to look at this figure, total distance is A2 plus B3. Do you agree with me? And this relationship should be valid for all the values of theta 2. Do you agree with me? So the distance between this frame and this frame is A2 plus B3. Now there is a subtle difference. Here there was a prismatic joint. That prismatic joint cannot rotate but can extend. The extension is given by d3. But the distance between these two frames, they are a2 plus d3 when theta 2 is equal to 0 in x direction. But you may have a case where you have a non-zero d3 and you have a non-zero theta 2, which means here you are going to have a2 plus d3 cosine of theta 2, a2 plus d3 sine of theta 2, and last term, since these are aligned, will be 0. Everyone understood this? I repeat this once again, and I want you to understand. In this particular case, even though we translated the frame, the fundamental logic remains the same. Distance between frame 3 and frame 2 along x2, y2, z2. Our x3, so here is x3, here is basically here is the frame x3, there is the frame the frame 2, and distance between these two is the addition of a2 plus d3. So this will be a2 plus d3 cosine theta 2, a2 plus d3 sine theta 2, and this will be 0. Are you with me so far? So actually, just second. No, yeah. I made a mistake here. My apologies. I made a mistake here. So this is going to be 0, 0, and the last one, a2, yeah, correct. a2 plus d3. A2. Sorry, I made a mistake here. Just please understand. This will be 0. This will be 0. So check this out. That is distance between frame 3 and frame 2. So frame 3 and frame 2. We already took care of theta 2. So we are just looking at the distance between frame 2 and frame 3. And the distance is along Z. It will be A2 plus D3 along Z2. Okay, just make a note of that. And now these are the homogeneous transformations. Now in the next part, what we have to do is we have to go to MATLAB and implement that code. So everyone understood how we got these homogeneous transformation matrices? The first homogeneous transformation matrix is between 1 and 0. Second homogeneous transformation matrix is between 2 and 1. Third homogeneous transformation matrix is between 3 and 2. And everyone understood what I made a mistake here. This is not cosine theta 2 or sine theta 2, because we have to find the distance along C2. We took care of the rotation already. The rotation is taken care of in the rotation matrix. So the frame is rotated. Only thing is now what we want is we want the distance between the frame rotated frame 2 and frame 3. Yes.
While calculating the 1h2, are we also assuming that the second coordinate or second frame is also rotating along with the first one?
Yeah. So basically, what we have is, so when you have the rotation, you have the rotation matrix between frame 2 and frame 1, which means frame 2 is on top of frame 1, but there is a relative rotation which is given as theta 2 that can rotate. So it is on top of it, but it has relative rotation. Does it make sense?
Okay, but then, wouldn't there be some distance associated?
There is no distance because the center point, origin of x2, y2 and z2 coincides with the origin of x1, y1 and z1. So there is no distance, but there is relative rotation.
Okay,
So once again, let me explain. So if you see here, this frame is x2, y2 and z2, and this is the rotation between frame number 2 and frame number 1. You agree with me? This is the rotation between frame 2 and frame 1. This is the projection between frame 2 and frame 1. But when you go here, since frame 2 is on top of frame 1, there is no translation distance. It's no translation. Yeah.
so if A2 is variable, what?
A2 is not variable. A2 is
If
constant.
if it is variable, what is?
So if A2 is variable, then you are going to have a different case. You will have an rotation matrix. So you will have a revolute joint, prismatic joint, and prismatic joint. So that will be R, P, P type of case. And there are two cases possible in RPP, and I will discuss those in just 2 minutes.
I mean, if there is a prismatic joint,
Let's solve that. So I understand what you are trying to say. So imagine there are two cases possible. So one case is you have a revolute joint. Then what you have is you have a prismatic joint, right? And then on top of it, you have another prismatic joint. We agree with, so this is a prismatic joint. So this is R, this is P, this is P. The other case is also possible. And that other, actually there are multiple cases possible. And we'll try to solve, I guess we'll see how much time we have. Be happy to solve all of this. So you have one prismatic joint. And then say you have another prismatic joint. This prismatic joint can be something like this. And you have another prismatic joint. And here you can have something like this. Or you can have any other combination. This could be the first prismatic joint could be horizontal and the second prismatic joint could be vertical. So all these cases are possible. We will set up, let me solve this problem first and then I will try to set up these two problems. Okay. Okay, so the next part is what I want to do is I want to go to MATLAB. And please go to RRP. And run this code. I will so online students, can you see my screen? This is the code. Once you go to MATLAB, so first clear all, then next I have theta1, theta2 and d3. So these are the three variables, theta1, theta2 and d3. I'm just specifying the value of a2 and a1. These are just the constants. Now what I want you to do is I want you to quickly take a look at my 0h1. Is that same as what we derived? 0h1. H12, 1h2. and H23. Can you see that? So can you see that in H23, I have in 0, 0. Then what I do is I perform the multiplication and then I simplify and then I get the expression for the end effector position. And next thing is I want to solve the forward kinematics problem when the value of theta1 is 0 degrees, value of theta2 is 35 degrees, and value of extension d3 is 170. Theta1, theta2 and extension. So these are the values. And I want to find out the end effector position and orientation. And in the last step, what I want to do is I want to compute the inverse kinematic solution, which is exactly same as what we have done in the last problem. Any questions about the code? So in the first step, I get 0h1, 1h2, 2h3, multiply them together, get the value of px, py, and pz. Then I substitute the value of theta1, I substitute the value of theta2, then I substitute the value of p3. Find out the px new, py new, and pz new. And then I try to find out the inverse kinematics. Given the values of px new, py new, pz new, what would be the values of theta1, theta2, and d3? Everyone understood this? So once you run this code, then it will solve the problem and then you'll be able to get. Can you see the solution is same as your input? Please run this code and make sure that you are getting the same solution. Everyone understood this? We just have the forward kinematics. We don't have to do forward kinematics next one. Forward kinematics is simple. Inverse kinematics is difficult. That's why we use MATLAB. Any questions on the code? Do you need me to explain the code? Again, everyone understood? Please understand, there is a little mathematical, there is a little variable jugglery here. This variable jugglery I'm doing because it's a symbolic substitution. You have a symbolic equation, you're substituting the numeric value, finding the numeric value, and then getting back the value of the variable. This code would remain same no matter what robot arm is solved. And let me tell you, you cannot solve inverse kinematics for more than 3 joints. You cannot solve inverse kinematics for more than 3 joints. If you get a robot arm that has 4 or 5 or 6 joints, what you have to do is, first you have to separate first 3 joints. You can only do inverse kinematics for 3 joints at a time. Why? Because you have px, py, pz, only 3 equations. So to find meaningful values of inverse kinematics, you have to consider only 3 joints at a time. And we will work on the problem. For example, in your homework, there is a Puma problem. Puma is the spherical wrist attached with the R robot. So I will solve the spherical wrist problem in today's class or next class. But if you have a 6 degree of robot problem, forward kinematics, no problem. Inverse kinematics, you have to split the last 3 and first 3. Everyone understood this? Because finally you only have 3 equations, px, py, pz. You cannot solve 4 or 5 unknown. Everyone understood this? So now let me take this problem. What I'm going to do is, let me work out So let's see. Let's so say all of a sudden you get a robot that you don't know about, okay? So we have these two robots configuration. And these are the robot configuration that you just gave me. Which robot configuration do you want me to solve?
Actually not.
Don't want me to solve any of these?
No, I have like another topic.
Okay, tell me.
What if A2 is variable in the sense if A2 and D3 both are variable?
If A2 and D3 both are variable, if something is variable, that's a joint.
Right, if there is only a prismatic joint along with it, but it's attached to a revolute joint.
Prismatic joint attached to a revolute joint.
We have to change in distances. Not here, we take change in the distance. So remove the prismatic joint.
So
I think we will change, right? So we take it as just the number or less than.
So every time whenever you get a robot, before kinematic diagram, you have to identify anything that is varying, that is a joint. There are two types of variations possible. One is the linear variation and other one is angular variation. As a matter of fact, if you have a spherical joint like a shoulder, what we do is we approximate the shoulder joint at the first revolute joint, second revolute joint, third revolute joint on top of each other. So for kinematic diagram purposes, we have to split the robot arm into prismatic joints and revolute joints. You won't be able to perform the kinematic analysis considering prismatic joint and revolute joint, everything at the same time. If you have a revolute joint on top of a prismatic joint, if you have a revolute joint on top of a prismatic joint, for analysis purposes, you would assume that there is some distance between the revolute joint and the prismatic joint. How do you consider, whether you consider revolute first, prismatic later, prismatic first, revolute later, that's totally up to you. But for kinematic diagram, you have to assume that those two joints have some finite distance. And at the end, when you work out the problem, once you get your forward kinematic expression, set that distance is equal to 0.
Oh. So for purposes of analysis, we break it up, but is that the distance?
At the end, you expect the distance is 0. Okay, now the choice is yours. You want me to discuss any robot arm that revolute, prismatic is simple.
Dr. Rector, I just have one last question. So if you take like linear motion, right, of the joint. So do I have to take the distance and the offset to the distance, like D2 plus H, or just like D2 is enough to take both in one?
Yes, so there is a case wherein what you have is you have offset not along one direction, but you have offset along two directions. In that case, that's not a problem. What you will do is you will treat everything here as per your convention. At the end of the day, whatever the distances are, you have to resolve those distances in the frame corresponding to previous joint. So let me give an example. Say imagine you have the robot arm which is not aligned. Robot arm which is like at an angle. So how would you do it? This robot arm which is an angle will have a projection along X and projection along Y. They will go over there. So even if you have a robot arm, even if you have the arm that is at an angle, remember, fundamental rule is you have to have that distance, the displacement between the frame results in the previous frame along axis x2, y2 and z2. No matter how those two frames are located, at the end of the day, you have to stick to your basic coordinates. Everyone understood that? Okay. Any robot arm that you want me to solve? Second, first. Okay. Tell me. Last call. Second. So actually, first robot arm is super simple. Okay. First, there is not much fun in first robot arm. So, Let me tell you. Many a times, you can just look at the robot arm and you would be able to tell what the forward kinematic is going to look at. Okay, so basically, so first robot arm, I want you to build this intuition. You agree with me? This is a revolute joint. What this revolute joint will do? This is revolve this lever arm. You agree with me? There is this prismatic joint and this prismatic joint. Prismatic joint can't rotate. The only thing that is possible is this would extend and this would extend. You agree with me? Which means at the end of the day, no matter what you do, the z distance is always going to remain constant. Z distance is not going to change. You agree with me? Okay. So which means if I want to write the forward kinematics, this is my end effector. This is my end effector. I know for the fact, no matter what happens, end effector distance A1 is going to remain constant. So I'm going to say Px, Py, and Pz. You agree with me? Pz will always be A1. Everyone understood? Now what I want you to do is, I want you to look from top. If you look from top, this is the center. And this is the displacement of the first prismatic joint. This is the displacement of the second prismatic joint. So this is going to be D2 and this is going to be D3. So this is D2 and this is going to be D3. Are you with me?
It's fully stretched always when we take it into consideration. There's no.
So you can treat D2 is equal to 0, D3 is equal to 0, which means they're fully contracted. Or they could be fully stretched. That's totally fine.
So the thing is, the variable will capture everything.
Yes, variable will capture everything. And then please understand, every time you do a coordinate transformation, always it has to be positive. Curl your finger in the direction of the z axis. This is your z naught. This is your x naught. This is your y naught. Can you see that this is going to be theta 1? So which means Px, can someone tell me what this will be? D2 plus D3 cosine theta 1 D2 plus D3 sine theta 1. Are you with me? Forward kinematics done.
Even the second, this might not redundant because it's not directly.
It's not irrelevant. But since I drew it like this, I just wanted that one. Now the question is, how would you solve the inverse kinematics problem for this guy? To solve inverse kinematics problem for this guy, clearly there is no inverse kinematic for. Basically, no matter what you do, it's going to be A1. You take the ratio of Px and Py, or basically take the ratio of Py by Px, and what you get is the tan theta. So that gives you the value of theta. And then you substitute the value of theta and you get the value of Px. And this Px can be achieved by any combination of D2 and D3. So this distance could be 2, 3, 3, 2, 5, 4, 4, 5. Anything is possible. So inverse kinematics is just a simple ratio. Everyone understood this? I'll explain this once. So here, if I give you Px is equal to 5, Px is equal to 5, and I give you Py is equal to 3, then what would you do? Py divided by Px. Py divided by Px is D2 plus D3 sine theta 1 divided by D2 plus D3 cosine theta 1. So which means this cancels and you can get the value of theta 1. Do you agree with me? Once you find the value of theta 1, please understand, you will do Px divided by cosine theta 1 is equal to D2 plus D3 and Py divided by sine theta 1 is equal to D2 plus D3. Are you with me? And basically, you will get the value for D2 and D3. And you will understand those cannot be uniquely written. You have to fix one and then get other. Okay, any other questions? Now, let me see, in this problem, actually, in this problem also, we can work out the forward kinematics just by looking at it. Yeah, tell me.
How do you set up the transformation matrices when you have a global origin that's offset in the global origin?
Move the origin, where the origin of the robot is. That's it.
So. If you guys calculated an inverse kinematics for every method, like the cities, like how they're not like, sorry,
No.
what is the ratio?
Yeah, so basically, there are multiple, there are two tricks that are. First, what you do is you take the ratio, or you square and add, or you convert sine into tan formula. So for example,
Now we have that from.
so, but the problem there is, it's not unique for every problem. Which means depending upon what the translated or trigonometric relationship you get, use the simplification technique. So I used to teach, there are two major simplification techniques. I used to teach simplification techniques, but then what started happening is, it's not like the rotation matrices and it's not like, I cannot say that this is the simplification you use for this. So one simplification would work for this problem, other simplification would work for other problem. At the end, you use MATLAB to solve. Might as well, MATLAB can use the polynomial substitution and solve this problem more efficiently than we could. And then you can't just use tan, because tan will just give you angle in one coordinate. You have to use arctan, a tan, that will give you tan in two coordinates. MATLAB does all that. So basically, you use the MATLAB solve function, and it will give you the answer. Okay, now what I want to do is, okay, now since you have seen so many problems, I'm going to give you some distances, okay? This is distance A1, this is distance D2, and this is distance D3. A1, D2, and D3. Can someone tell me what is the work envelope of this robot? Which means, how would this end effector move? What is the workspace of this robot? This is a cylindrical workspace. Can you see that? No matter what you do, at the end of the day, that end effector is gonna go in the cylindrical. Okay? Everyone understood this? Now, what I want you to do is, I don't want you to write the homogeneous transformation. You can write those, you will get correct answer. But just looking at the robot, can you tell me how would you solve Px, Py, and Pz? So for an example, first let's identify the coordinates. This is Z0, this is X0, this is Y0. Do you agree with me that the Z direction, so Px, Py, Pz. You agree with me? Pz, no matter what you do, will be A1 plus D2. You agree with me? Now, what happens to Y and X? Now, if we look at X and Y, you look from top. And what do you see? You see just D3, right? And this angle is theta 1. So do you agree with me? Px is going to be D3 cosine theta 1. Py is going to be D3 sine theta. Are you with me so far? So, how would we get the inverse kinematic solution? Inverse kinematic solution for this can be uniquely determined. So, if I give you Px, Py, Pz, you will take the ratio of Py by Pz, get the value of theta 1. From Pz, A1 is a constant, you will get the value of D2. And you will substitute sine theta 1 and then that will get you the value of D2. Everyone understood this? You can solve the inverse kinematics problem for this robot uniquely. Any question?
Frame assignment, how it is.
Hmm?
The frame assignment.
Oh, frame assignment. Actually, you may have to translate the frames. But since you asked, so let's start. This is going to be Z1. Now, oh, this is not too bad. This is going to be X1. And this is going to be Y1. Can you see if the rule is satisfied? X1 is perpendicular to Z1. X1 is perpendicular to Z0. Right hand coordinate rule satisfied. Now comes the next question. Here, you are gonna have Z2. Now let's look at X2. X2. Oh yeah, X2 here also is no problem. X2, and then since my X2 is here, Z2 is here, my Y2 will go on. And on my end effector, I will copy the same direction. Y3, Z3, X3. So, good news is I don't think we get frame rule violation here or here.
The second plus 100.
Hmm.
That is moving towards.
Right. Z, because this shows the direction of the.
So is that axis?
Any questions?
Can you tell me how the Tx equal to T3 cos theta?
Px, okay. T3.
That angle is actually
The only joint that can rotate is first prismatic joint, first revolute joint. This is the prismatic joint, which means up and down, forward, backward. This cannot rotate. The only joint that can rotate is this. Look from top. Look from top. What do you see? You see a circle, right? And what is this? This is the radius of the circle, and this is the projection of the circle.
Sir, what if we have a rotary joint like this and the settings is like this? The frame assignment.
Okay. Now you have to tell me, since you got me started, first revolute joint, so tell me, first revolute joint perpendicular,
Yes. First is like this.
parallel, okay?
Yes. The second is
Second is,
like this.
so this revolute joint goes up. Second revolute joint is like this, right? Is that what you're saying?
Sir, in this area, in the horizontal.
Oh, come on, that is super simple. So this like this, right?
No, sir, no.
Okay, like this.
On the in a straight line, not on the vertical side.
Okay, first let me draw the, okay. This is my first revolute joint. Okay, this is the joint action. Now tell me,
I think it's showing the,
yeah, you can draw it on the board here,
I am the book, I think.
okay? Is that a homework problem?
Yeah.
Oh,
Basically like this. I think it's really the same.
First is like, the second is.
I was gonna solve that problem. That's a straight of this. Okay. This is this, and then what you have is. Oh, come on. So basically, what you have is. right? Okay, before I go to this problem, this is the spherical wrist problem. You have R perpendicular to R perpendicular to R. So this is R perpendicular to R perpendicular to R. So that's what is called as spherical wrist. This is a spherical wrist problem. And remember this problem because robotics 2 begins with this. Every aircraft is a spherical joint. From kinematics point of view, the frame that describes the aircraft motion is a spherical joint. Aircraft can yaw, can pitch, and can roll. Aircraft can yaw. Let me see. So this problem is extremely important, and I would like to discuss this in detail. But before that, I just want to make sure that you understand. In my robotics 2, I start with this plane. Spherical wrist determines the rotation of the aircraft. Aircraft can yaw, roll. Basically, can you see the first revolute joint? Then aircraft can pitch. Can you see the second revolute joint? And the aircraft can roll. Can you see third revolute joint? And these three revolute joints are perpendicular to each other. That's why this is called as the spherical wrist. Now, if you look at your Puma robot, which is one of the homework problems, the very first robot that we saw in the last class, R parallel to R, perpendicular to R. Combine that with a spherical wrist and you get your Puma robot. Everyone understood this?
Not about the Puma.
Huh?
I
What about Puma robot? Okay. The last class, the first problem that we solved, that we had a revolute joint. Then we had another revolute joint, and we have one more revolute joint. So R perpendicular to R, parallel to R. Remember, if you combine those 3 degrees of freedom articulator or manipulator with a wrist, which is R, you get Puma robot. So when you work out the forward or inverse kinematics of Puma robot, see, to be honest with you, all the homework problem I'm going to solve in class. What you need to do is just mix and match. So you take the forward kinematics of the first robot that I have solved and forward kinematics of the spherical wrist that I'm going to solve, and you get the solution for Puma robot. Everyone understood this? So I want to talk about this problem in detail, but there is one robot that I would like to discuss, which is the Sierra robot. The reason I want to discuss Sierra robot is we will have, after your first 5 labs are done, I want you to move on to a commercial robot. We have a robot M1 commercial Sierra robot that I want you to work on. So I will work out the spherical wrist, but please understand, if you are going to take robotics 2, spherical wrist is the cornerstone of aircraft motion, aircraft kinematics. Because once again, first revolute joint is yaw, aircraft can yaw. Second revolute joint, can you see aircraft can pitch? And third revolute joint, aircraft can roll. So it is yaw, pitch, and roll. Everyone understood this? Yaw, pitch, roll. Okay, before I solve this, what I want to do is, and I want to actually work out one problem, which is the Sierra robot. If you look at the Sierra robot, in Sierra robot, what you have is, you have a revolute joint. Then this revolute joint is attached to another revolute joint. So this is attached to the second revolute joint. And then this second revolute joint is attached to a prismatic joint. And this prismatic joint has the joint articulation about this side. So you have this revolute joint this revolute joint and this prismatic joint. Do you agree with me? Okay. Now, since I showed you two robot arms, can you tell me the forward kinematics of this robot just by looking at it? So I will get you started. So this is Z0, right? This is Z1 and Z2 could be up or down, right? So Z2 and then, okay, so here this is going to be X0, this is going to be Y0, again this is going to be X1, this is going to be Y1. Are the rules satisfied? Okay. Now what about Z2? What about X and Y? So I would say, unfortunately, in this particular case, which way should the X be? Can it be in this direction or can it be in this direction? Everyone agrees that my X2 should be like this. So X2, Z2 and Y2. Are you with me so far? Last X2, Z2, Y2. You agree with me? Now let me give you these dimensions. A1, A2, then A3, and this distance is going to be this should be actually D3. So this distance is, so from end effector here to here, this distance is going to be Are you with me so far? A1 is a constant distance, A2 is a constant distance, A3 is a constant distance, but this D3 would be changing because there is a prismatic joint that can go up and down. Everyone understood this? Yeah.
Even if we take Y2, like in place of Y2, if we take X2, then also it will be perpendicular to both Z1 and Z2.
No. If X2 is in here, then X2 will be perpendicular to Z2, but X2 will be parallel to Z2. It's not going to intersect. Can you see that Z1 is going like this and X2 is going like this?
Okay, so in this case, we should not.
This has to be X2.
No, I mean the frame for the prismatic joint should not be.
There is, you should only translate the frame if the rules are not correct.
Okay.
Can you see that when we chose X2 to be towards right, the rules are correct? No need to pass. Everyone understood this? Now I want you to look at this problem and first and foremost, tell me what would be the distance between the 0th frame and this is the third frame, X3, Y3, right? So E3, Y3 and X3. So what would be the distance between the 0th frame, the first frame, second frame and third frame? So tell me what is Px, Py and Pz. Yeah. So one thing that I want you to remember is look at the extension of joint, and this is very important, something to keep in mind. Can you see the joint extension in this direction? Can you see that the joint extension in this direction? So which means A1 is positive, but joint extension is negative. Are you with me so far? Okay, look at the arrow, Z0 arrow. Can you see Z0 is going up, but this joint is going down. That's why this has to be negative. Now Px, can you see? Now I want you to understand. Look from top. Oh, there is a distance. Okay, then you can add the distance. You are right. So there is a distance. I'll ignore the distance. Call it A4. Just A4. Okay. Now what I want you to do is, I want you to look from top. Can you see that this is the first revolute joint, this is the second revolute joint. So if you look from top, this is just like a pendulum, compound pendulum. Remember? So this is theta 1 and this is, actually I need to draw properly. This is theta 2. And this is A2 and this is A3. Remember everyone, Px is going to be A2 cosine theta 1 plus A3 cosine theta 1 plus theta 2. Right? And Py is going to be A2 sine theta 1 plus A3 sine theta 1 plus theta 2. Are you with me so far? Everyone understood this? I gave you the answer, but in your homework, I want you to work out the forward and inverse kinematics. I mean, the forward kinematics. I have given the MATLAB script. This is the Scala robot. I have given the MATLAB script that solves Scala robot. So if you go on to Canvas, in the last 1 minute, let me show you. If you go to Canvas, I want you to go back to modules and then go to Scala.m, download Scala.m, open Scala robot, and then what you will have is, you will have these H0, H1, 1, H2. At the end, what I want you to do is this. Graph from here to here. And basically what you will have to do is, you have to say here simplify. Otherwise, you are not gonna get a clean and nice equation. So what I want you to do is, graph from here, go all the way over here. So I gave the values for the A0, A1. Okay, but I think you should be able to see this easily. So can you see A1 cosine theta 1, A2 cosine theta 1 plus theta 2, which is Px. Py is A1 sine theta 1, A2 sine theta 1 plus theta 2, Py. And Pz is 200, which is the offset minus. So whatever we derive from the intuition or looking at the kinematic diagram, we get the exact same answer from doing the homogeneous composition. So we'll stop here. Yeah, I will work out the spherical wrist completely in next class. but spherical wrist solution is uploaded onto canvas and spherical wrist code is in the module. So if you want to take a look at it, that- can, yeah, one file is good enough. Yeah. Yeah, tell me.
Sir, here you are taking this as in the initial problem, you are
Yeah.
adding up these two lengths, no, sir.
Yeah.
But